Welcome to our lesson about molecular forces. So this is actually something we did cover a bit in grade 10. We're just going to expand upon it a little bit, and it's another topic that we're going to visit again in grade 12. So really, this unit, we're talking about chemical bonds, and this is really the basis behind those chemical bonds is those molecular forces. So let's take a look. We have two types of molecular forces. Let's start with the first type. The first type of molecular force is called intramolecular forces. So you can see this A here. I always like to remember intramolecular forces because I think of like intramural sports. So if you're playing intramural sports, if you're in an intramural dodgeball league, that means that you're playing other students within your school. So intramolecular forces are between atoms in a single molecule. So intramolecular forces are forces between atoms in a single molecule. So let's think about this. We might have an oxygen molecule. So we might have one oxygen, and then we might have a hydrogen and a hydrogen bound to it. That's going to make us a nice little water molecule there. And what an intramolecular force would be, it would be these green bonds that are actually holding that oxygen to that hydrogen and that oxygen to that hydrogen. So intramolecular forces are within one single molecule. All right, a little bit of an important thing to understand, and we've already talked about it once, but I want to bring it up again. That's electronegativity. So just a reminder of what the definition of electronegativity is. Electronegativity describes the relative ability of an atom to attract electrons. So if an atom has really high electronegativity, it is likely to attract electrons. If an atom has a really low electronegativity, it is likely to lose electrons. So we talked about that in periodic trends. Why are we talking about electronegativity now? The nature of a bond is actually based on electronegativity. So based on the difference between electronegativity of two different atoms, it's going to tell you what type of bond you have. So we're actually going to use electronegativity to determine bond type. So I'm going to zoom out a little bit, and I'm going to show you this kind of number scale. So here we actually have three different bond types. We have nonpolar covalent, we have polar covalent, and we have what's called ionic bonds. You actually probably remember the term ionic bonds in grade 10 chemistry. We talked about ionic compounds. An ionic bond is just what holds together an ionic compound. And then you see the word covalent. You probably remember the word covalent bond from grade 9 and 10. If not, you might have heard the word molecular instead. We talked about molecular compounds. Molecular compounds are between two nonmetals. A covalent bond is just what holds together molecular compounds. So the only difference in grade 11, we're still looking at covalent bonds and we're still looking at ionic bonds. The only difference is we've divided these two covalent categories into what we call nonpolar covalent and polar covalent. So I'm going to give you an example in a second of the difference between nonpolar and polar covalent, but we actually have a whole different lesson that we talk about polarity in. So I'm not going to worry too much about the difference between nonpolar and polar now. I'm going to worry about categorizing them now, and I'll explain in a whole separate lesson exactly what polarity is and exactly how it works. Again, in grade 10, you could tell the type of bond by just saying metal, nonmetal, or nonmetal, nonmetal, right? So an ionic bond was a metal and a nonmetal, and a covalent or molecular bond was between two nonmetals. Now we're going to take it one step further, and we're going to be a little bit more accurate. So we're going to be a little bit more accurate. Instead of looking at the types of atoms that we have, we're going to use numbers instead because chemists love numbers, and we're going to be looking at the differences between electronegativity. So if the difference is greater than 1.7, if it's a really big number, we consider it to be an ionic compound. If it's between 0.4 and 1.7, if it falls between here, we're going to classify it as polar covalent. And if it's less than 0.4, we're going to classify it as nonpolar covalent. Okay, so let's take a look at an example. And our example is going to be nitrogen and a nitrogen bound to 3 bromines, so nitrogen tribromide. So we're going to try to classify whether or not nitrogen tribromide is an ionic compound, polar covalent compound, or nonpolar covalent compound. In order to tell this, I need to list the electronegativities. I don't like that green. That's too bright. Let's go to blue. We need to know the electronegativities of nitrogen, and we need to know what the electronegativities of bromine are. Now, you might understand the trend for electronegativities. That's great, but here you have to know the specific number. So I want to point something out to you. I want to point out on your home page. So your home page looks like this. On the side of your home page, you have a bunch of widgets over here. So you're going to see a periodic table widget. You're going to see an electronegativity widget. That's the one that we want right now, is that electronegativity value. So I'm going to click on this widget, and that's going to bring up a chart of all the different types of electronegativity values. So this chart is going to be what we're going to use to actually determine our electronegativity differences. So we're looking for the electronegativity differences between nitrogen and bromine. So I have to find nitrogen in this chart first. I found it right here, and it's a 3. So I'm going to go ahead and I'm going to write the value 3 here. And then I'm going to go back and I'm going to find bromine on that chart. So if I go back here and find bromine, bromine's right down here, and it's 2.8. So I'm going to go ahead and I'm going to write 2.8. Now, this is sometimes where students get confused because there's like, well, there's 3 bromines, so do I have to multiply by 3? No, and I'll show you why. So what we care about is I'm just going to sketch kind of roughly what this molecule looks like. Looks roughly like this. I'll show you a much better sketch when I show you how to draw Lewis diagrams, which is going to actually be the next lesson. So what we actually care about is we care about this bond. We're trying to classify this bond right here. We're trying to classify the difference between nitrogen and bromine. The idea is if they have really similar electronegativities, it's like a tug of war, and they're going to equally pull on electrons. If one has a much higher electronegativity, it's again like a tug of war, but one's going to be much stronger. It's going to pull the electrons towards it. So in this case, we're going to go ahead and we're going to subtract 3 from 2.8. And if we subtract 3 from 2.8, we're going to find it's going to give us a value of 0.2. If I scroll back up here, oh, my numbers came with me. That's fun. If I scroll back up here, 0.2 actually falls in this part of the number line here. So since 0.2 falls in this part of the number line here, we would classify it as nonpolar covalent. So for nitrogen tribromide, we would say our final answer would be that this would be nonpolar. Instead of writing nonpolar, I'm just going to write NP, nonpolar covalent bond. So I'm just going to write cov, because you don't want to see me use this weird pen to write that entire thing out. This is going to be an example of a nonpolar covalent bond. All right, so now that we understand that example, why don't you go ahead? I'm going to have you pause the video, and I want you to try a couple of these examples on your own. So again, you're going to be using that electronegativity chart. I want you to try to go ahead, try to figure out the bond type for each of these. And once you figure out the bond type for each of these, come back and we'll see if we got the same answers. So I'm going to assume you pause the video. I'm just going to keep going. So let's take a look at hydrochloric acid here, HCl, hydrogen chloride. So we're going to need the electronegativity value of hydrogen, and we're going to need the electronegativity value of chlorine. So again, if you look at that chart, you're going to see that hydrogen has an electronegativity value of 2.1. And if you look at chlorine, you're going to see that it's got an electronegativity value of 3.0. So if we go ahead and we subtract these two numbers, we're going to find a difference of 0.9. Now, if it's 0.9 difference, this is more than 0.4, but it's less than 1.7. So it's kind of that in-between ground there. That in-between ground there, we call that a polar bond. Again, I'll get more into what polar means in a different lesson. Here we have chromium oxide. So in this case, CrO. So we're going to go ahead. Cr has an electronegativity from that chart of 1.6. And oxygen from that chart has an electronegativity value of 3.5. So if we go ahead and we subtract those two values, we're going to find that the difference between them is 1.9. What you're going to find is 1.9 is over that 1.7, so we would call this an ionic compound. Now, based on your grade 10 classification, you would have noticed that Cr, chromium, is in fact a metal. Oxygen is a nonmetal. So based off what you learned in grade 10, you would still classify this as an ionic compound. So you were right with making those assumptions in grade 10. This is just a little bit more accurate because it allows us to talk about the difference in electronegativities and how strong the bond is, which is going to be important as we move forward. Bromine, this is an easy one. So we're going to do the math on this one once, and then I'm going to show you the shortcut. Bromine, I guess I should probably write Br first, right? Bromine has an electronegativity of 2.8. Now this 2 tells me that this bond is between two bromines. So I have a bromine and I have a bromine bonded together. So technically what I need to do to find the electronegativity difference of this bond is I need to take the electronegativity value for bromine and the electronegativity from bromine and go ahead and subtract them. So if I take bromine and I minus bromine, I'm going to get an electronegativity difference of 0. They're the same number. So this is going to be an example of a nonpolar bond. In fact, anytime that I have a Hofbrinkel, anytime I have a diatomic element, the same element in a bond, it's always going to be a difference of 0. It's always going to be a nonpolar bond. Last up, we have water. So hydrogen has an electronegativity of 2.1. We already did that one. And oxygen we've already looked at as well too. Oxygen has an electronegativity difference of 3.5. So if we go ahead and we subtract those two values, we're going to get a difference of 1.4. That falls in that middle range, so we would also consider this to be a polar bond. So pretty easy to classify which bond is which, right? Just a little bit of math, just punching them in on your calculator. Now we're actually going to look at defining each of these bonds and what they mean. All right, so let's talk a little bit more about covalent bonds. So I used the word covalent bond before. Let's talk about what a covalent bond actually means. So a covalent bond is characterized by the sharing of electrons between two or more atoms. So in this case, electrons aren't necessarily stolen. That's a word I used in grade 9 or 10. We don't see a transfer of electrons. Electrons are shared. That's because the electronegativity difference isn't great enough to actually see an electron get lost. So let's think about, we talked about hydrogen and oxygen before. We talked about water. That's an example of a covalent bond. It's a polar covalent bond. We just classified that. So what's happening here is oxygen has a higher electronegativity than hydrogen does, right? Oxygen has an electronegativity of 3.5. Hydrogen only has an electronegativity of 2.1. So what's happening is the electrons in oxygen are wanting to spend slightly more time with oxygen, but the difference here isn't big enough to actually have oxygen steal hydrogen's electrons. So oxygen isn't a big enough difference to actually steal the electrons, so instead it just shares the electrons. In this case, it's unequal sharing. I'll talk about that a little bit more later, but a covalent bond is characterized by the sharing of electrons, not the stealing of electrons. It tends to be between nonmetals of two atoms of the same element or elements close to each other on the periodic table. So again, in grade 9 and 10, when you were categorizing covalent bonds, you were just saying if it's nonmetal, it's covalent. Well, let's think about what we know about the periodic table. Elements with similar electronegativities are going to be close to each other, right? They're going to be close to each other on the periodic table. If they have very, very, very different electronegativities, they're going to be on opposite ends. So elements that are close to each other on the periodic table, those are all nonmetals. They're very close to each other on the periodic table. I'm sure some of you might have the question now, well, why don't metals form covalent bonds? Why don't metals, which are also close to each other on the other end of the periodic table, form covalent bonds? I will answer that question in grade 12. So in grade 12, we'll talk about metal-metal bonding. Right now, we're only talking about the other side, nonmetals. And nonmetals are close to each other. They have similar electronegativities, so that means they're going to share electrons. So two atoms with similar electronegativities will not exchange an electron, so they won't steal an electron from their outermost shell. They'll instead share that electron. Let's talk about the other type of intramolecular force now, and that's ionic compounds. So ionic compounds occurs when there's a large difference in electronegativity. So it means that the difference in electronegativity is greater than 1.7. So let's think about another ionic compound that we saw. That was chromium and oxygen. So we had chromium and oxygen. We categorized that one as well too. Chromium had a 1.6 electronegativity, and oxygen had a 3.5. So what that means is it means it's quite a large difference. Since it's quite a large difference, oxygen actually has a strong enough electronegativity to win the tug of war and actually steal that electron. So oxygen is actually going to take an electron. So we're just going to draw a little arrow, negative sign for electron. Oxygen is actually going to take chromium's electron, and in this case, you actually see the exchange of electrons. This is going to lead to the loss of an electron from the less electronegative atom. So whatever has a smaller number is going to lose the electron, and this is going to result in two ions. So since an electron was lost here, we're going to have a positive charge. Since an electron was gained here, we're going to have a negative charge. These oppositely charged ions feel an attraction to each other, and this electrostatic attraction is what causes the ionic bond. So essentially, we know that opposites attract. So we have a positive here, we have a negative here, and this positive and this negative are going to attract. That's what's going to cause my ionic compound. Ionic bonding occurs between metals and nonmetals. So again, this is what you learned in grade 9 and 10. An ionic bond is a metal and a nonmetal. Now you know why though. It's because they're opposite ends of the periodic table. So we have metals, we have nonmetals. That means the electronegativity difference is going to be big enough that we can actually see the transfer of an electron. So now we've hopefully got a bit of a better understanding about the two types of intramolecular forces, ionic compounds and covalent compounds. Let's take a look now at intermolecular forces. So believe it or not, this is a different word than what we looked at. It's only one letter different though. So here we're looking at inter with an E. Inter is like intramural sports. So when you go to another school to play sports, that's intramurals. So intermolecular is between two different molecules. So intra was the same molecule within the same molecule. Inter is two different. So intermolecular forces are forces between molecules. They determine things like boiling point and the substance of a state. So all of those physical properties that we see, boiling point, melting point, whether or not it's a solid, liquid, or gas, that's actually determined by how strong the intermolecular forces are. So let's take a look at what I mean by this. We're going to look at our old friend water again. We're going to use the same color because it takes too much time for me to switch. So now, if we want to look at the intermolecular forces between water, we need at least two water molecules. And what an intermolecular force is within water is it's the forces, there are forces, believe it or not, actually attracting together these molecules. There's forces that are actually going to hold these water molecules together. They're going to kind of stick them together. It's going to glue them together. And depending on how strong those forces are, that's what's going to determine those different physical properties. So we're looking at between molecules now, not within molecules. So we have a couple different types of intermolecular forces that we're going to talk about. We're actually going to talk about three different types. We're going to talk about something called dispersion forces. That can also be called London dispersion forces, or sometimes you can hear it called van der Waals forces as well too. So this first one has lots of names. The second force is dipole-dipole, and the third force is hydrogen bonds. So how these are organized, these are actually organized from weakest down to strongest. So we're going to start with the weakest force and we're going to go to the strongest force. If something has very strong intermolecular forces, it's stuck together really well. These are likely solids, or these are things with really high melting points. If something has very weak intermolecular forces, they're not stuck together very well at all. Since they're not stuck together very well, they're going to have lower melting points, they're going to have lower boiling points, and they're more likely to be gases. So let's look at the weakest bond first, and that's going to be our dispersion forces or our London forces. Now this is actually kind of cool because it's something that happens in all molecules, and it's literally just change. So London dispersion forces are very weak forces of attraction between molecules, resulting in momentary dipoles occurring to uneven electron distribution. So kind of confusing. First of all, we need to talk about what that term dipoles is. But before we get to dipoles, I want to talk about what this uneven electron distribution is. So that uneven electron distribution, we know that we have a positive core, and we know that we have electrons kind of flying around this center, right? So we have electrons in orbit flying around this positive core. Now, every time we've drawn a Bohr-Rutherford diagram, we've always had those electrons evenly spaced out, and those electrons haven't been moving. That's not really true, right? In reality, those electrons are moving. So isn't there a chance that at any given time, the electrons might find themselves accidentally all on one side? Well, sure, of course, there's a chance that could happen. And that's what does happen sometimes. So what's happening here is an instantaneous uneven distribution of electrons. So instantaneously, these electrons all happen to find themselves on one side. Now, we use the word instantaneous because it doesn't last forever. As long as the second that it happens, essentially the next second, the electrons are going to go ahead and they're going to distribute themselves evenly again. So the fact that the electrons are on this side, it's going to cause this word dipole. So what a dipole is a dipole is like a charge. So since both negatives are on this side, that means this side is going to appear, oh, that's not what I wanted to do. Let's try that again. That means this side is going to appear slightly negative, right? We have both negatives on this side, so this side is going to be slightly negative. Since there's no negatives on this side and a positive in the center, this side is going to appear partially positive. So we have a negative side and we have a positive side. Well, what would happen if we have two molecules with dipoles? So here we have two molecules that have dipoles. I have a negative side, I have a positive side. Now notice this weird kind of figure 8 up here, right? It's a weird figure 8 that seems to be missing an arm, looks like that. That's how we draw a dipole. So we're gonna talk about that a little bit more in the next slide. So a dipole just means that it's not a permanent charge. It means that it's a charge for a second and that charge is going to change. So here we have our dipole, our negative, and we have our positive dipole. Well, what happens if this molecule comes across another molecule that has that same dipole, negative and positive? What's going to happen is this negative end and this positive end are going to attract. It's going to cause a bond. Now, the question is, how strong do we think this bond is going to be? Well, this bond is based on the fact that electrons instantaneously have an uneven distribution. Remember, this distribution is not going to last very long. So the second it forms, it's going to break. And as soon as this distribution that's not even breaks, it means this bond is going to break. So these are actually very, very, very weak bonds, and they're based sheerly on chance. So it's kind of molecules flying around, and a molecule finds another molecule that for that second has a different distribution, and they're attracted just for a second. So London forces or dispersion forces happen in everything, but they are extremely weak because they don't last, and they're based sheerly on that uneven distribution. So that's our weakest bond. Let's take a look now at our next strongest bond. Oh, I lied. I have a little bit more I want to say, apparently. So the more electrons that are present in a molecule, the stronger the dispersion forces will be. So here, we took a look at just 2 electrons, right? That's like 2 negatives. If we had had maybe 8 electrons on this side, it's going to mean a stronger negative charge and a stronger positive charge. So the stronger those charges are going to be, the stronger the forces are going to be. So the more electrons something has, the stronger the dispersion force is. Dispersion forces are the only type of intermolecular forces operating between nonpolar molecules. So when we looked at our bromine and our bromine before, right, that was our nonpolar molecule we looked at before. There was nothing else that was actually holding that molecule together outside of those very weak London dispersion forces. So anytime you're looking at a nonpolar molecule, nonpolar bonds are considered to be weak, and they're weak because they only have those London dispersion forces that are between them. Now let's take a look at our next bond, and our next bond is dipole-dipole interactions. So we've seen the word dipole before. Remember, dipole means a partial charge. So it doesn't mean a permanent charge, it means a partial charge. It's got that kind of weird figure 8. So the partial positive charge on one molecule is attracted to the partial negative charge on another molecule. It occurs between molecules that have permanent net dipoles or polar molecules. So again, I'm going to talk about the cause of polarity a little bit later, but a polar molecule has a negative end and it has a positive end. So for example, let's take a look at our HCl. We looked at our HCl before. We classified it as polar. So we have HCl. H has an electronegativity value of 2.1. Cl has an electronegativity value of 3.0. Since Cl has a larger electronegativity, what that means is in this tug of war, the electrons are going to want to spend more time with chlorine. Since the electrons are spending more time with chlorine, they're spending more time over here. This is going to appear that chlorine has a slight or partial negative charge. It's not a permanent charge because the electrons aren't spending all their time with chlorine. They're just spending more time with chlorine. Same idea, since hydrogen, the electrons are spending less time with hydrogen because they have a smaller electronegativity. We say this has a slight positive charge. Now again, it's not a permanent positive charge because they haven't lost those negatives. The negatives are just spending more time over here. So we have a slight negative and a slight positive end. Now this is based more than chance, right? This isn't just an uneven dispersion. This is because of a difference in electronegativity. So this is actually much more permanent. It's not a full negative charge. It's not a full positive charge. It's a partial charge. So what's happening here in a dipole-dipole interaction is those negatives and positives are sticking together. So a negative chlorine here is going to want to be attracted to a positive hydrogen here. A negative chlorine here is attracted to a positive hydrogen here. My positive hydrogen is attached to this chlorine, and this is going to cause our interaction. You can imagine, since it's not based by chance and these aren't broken consistently, you can imagine that this bond is actually considered to be a stronger bond. The larger the electronegativity difference is, the more polar your bond is, the stronger the bond is. Last one that we want to look at is our strongest bond, and this is our hydrogen bond. So hydrogen bonds occur between molecules that have a permanent net dipole. So again, we've got that word dipole, resulting from a hydrogen bond being covalently bonded together to either fluorine, oxygen, or nitrogen. So why do we pick fluorine, oxygen, or nitrogen? Because when you have hydrogen bound to one of these things, their electronegativity differences are so polar, it's almost ionic. It's not quite ionic, but it's almost ionic. It's a very, 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 very polar bond. It's so much stronger than the other polar bonds that it actually gets its own category. So we, for example, looked at hydrogen and oxygen before. Hydrogen has an electronegativity of 2.1. And oxygen, again, has an electronegativity of 3.5. So that difference is actually so large that the molecules spend almost all of their time with oxygen. Not all of their time, it's not permanent, but they spend almost all of their time with oxygen. That's going to make for a much stronger bond. And since you have that's going to make for a much stronger dipole. And since you have a much stronger dipole, you're going to have a much stronger bond. So it's the same idea as a dipole-dipole bond. Positives are attracted to negative ends. So my positive hydrogen is attracted to my negative oxygen. My positive hydrogen is attracted to my negative oxygen. My negative oxygen is attracted to my positive hydrogen. But since these are stronger dipoles, they just happen to be stronger bonds. That means anything that has a hydrogen bond is really tightly stuck together. So they really, really, really don't want to move. That's why things like water have higher melting points or higher boiling points when compared to other substances, because it's an example of a hydrogen bond. So now that we understand these forces a little bit better, we are going to look at two different things. We are going to take a closer look at that polarity idea, how to figure out if something is polar. But before we do that, we are going to take a closer look at how to draw these molecules. So I was just kind of sketching these before, that's great, but I want you to be able to actually draw them yourself. So we are now going to look at how to draw molecules in terms of Lewis structures.